Now we're looking at some more problems on partial fractions. So this one we've got three linear factors. And that's not a problem. We treat it in the way that we would just say x minus 2, x plus 2, and x plus 3 as our three linear factors in the fractions separated there. And again, they just have constants up top. Now what it does get harder is that you will have a larger expression when you put it back in the form when we to get a over x minus 2, x plus 2, x plus 3, we'd have to multiply it by x plus 2 and x plus 3. B has to be multiplied by x minus 2, x plus 3, and C would have to be multiplied by x minus 2, x plus 2. So that's a little bit more working in that regard that you have to do to get a common denominator again back from that to get an equivalent statement for x squared. But still doable. It's still doable. Now, what I want to do is look at a little bit different way of trying to find our constants A, B, and C. In this form, if I start to make x be equal to minus 2, now, nice thing starts to happen. If I sub x is equal to minus 2 into this part, well, that's going to make that 0, which means the part there with the A constant is going to be 0. With B, it's not 2. It's going to get minus 2, like we've got there, and minus 2 plus 3. So that's going to calculate. But putting minus 2 in this part here means that it's going to go as well. So that's going to become 0. So the C constant goes, x is equal to minus 2. So we put the minus 2 in for the left-hand side as well. And we've just got an equation now with a constant B in there. That's nice. That's what we want. We want equations with one variable. So we're able to solve down and get B is equal to minus 1. Similarly, if we let x be equal to minus 3, well, we sub it in for the left-hand side, but we said minus 3 in there, and that'll cancel, because that'll make it all 0. Subbing minus 3 in there makes this whole part 0, and so we can just put it into this part, and that'll allow us to find C. The C works out as 9/5. And then if we let x be equal to, there's minus 3, if we let x equal to 2, so again, this part would be 0, this one would be 0, when x is equal to 2, so the B and C cancel, and we can put 2 into the left-hand side as well, and we've got an expression there we can find A, and that allows us to get A as 1/5. So there's our three constants, 1/5 for A, minus 1 for B, and 9/5 for C. So we can write it like that. So again, it's not the same process for when it's 3, it's just a bit more work because you've got to find 3 constants in this case. This one's a little bit different now. We've got 1 over x plus 1 and x squared plus 4. Now, x squared plus 4 is not a linear factor, but also we can't reduce that down to a linear factor. So into two linear factors, it can't be divided. We're not going with complex numbers, so don't be saying, oh, well, you can go complex numbers. We don't do complex numbers with our partial fractions here. They've got to be real numbers. So if that's the case, that's irreducible. So what that means for us is when we go to our fractions, we get the A on x plus 1 because A is of degree 1 less than x plus 2. But because that's x squared plus 4 and it can't be reduced, then the numerator could be in the form bx plus c. So we've got to start to take that into consideration because that's 1 degree less than x squared. So we've got to consider our numerator can be 1 degree less than our denominator if our denominator can't reduce down to nice linear factors. Now, that's our aim, is to try and get nice linear factors every time, but it's not always possible. So can't be reduced. So we're back to saying, well, if I'd multiplied these two to give me the x plus 1, x squared plus 4, multiply A by the x squared plus 4 and multiply x plus 1 times bx plus c. So we get that. And that's all going to be equal to 1. It's equal to the numerator. Expand our brackets and collect our terms. So we get the x squareds together, we get our terms in x together, and we get our constants together. So for x squared, remember we're looking at equating these two because it's 0x squared technically on our left-hand side. So the a plus b would be equal to 0. So that's where that a plus b is equal to 0 from. So a is equal to minus b. And we could also say then as well that when a is equal to minus b, we can do the substitution back in there So, and we can end up with C being equal to 1 minus 4A. We can also have the situation where 0x is equal to B plus C. A lot of x, so B plus C is equal to 0 as well. So we can use our substitutions that we had for B and C, both in terms of A, and substitute in, and we're going to come down to get A is 1/5 once we do that substitution and solved. So if A is 1/5, then we're able to put it back that B must be minus 1/5, and C would be 1/5 as well, because 1 minus 4 lots of 1/5 will give us 1/5. So that's what it's going to look like. So we get the 1/5 there, or 1 on 5 x plus 1, and the 1 on 5 for minus 1 on 5 for B, so we could write like that times x plus the 1 on 5, which is for C. If we want to, you can write it down. It's a bit more neater to write it a bit like that, taking your 1/5 down the bottom. It'll be 1/5 on all of it there. So, but either way, we'd be quite happy to see. For question 7 here. Now, looking at this one, x cubed, so degree 3 up top, x times x squared, degree 3 in the bottom. So we can cancel, and this one's not a bad cancel, it's a pretty easy cancel. Because the x cancels with the x cubed, so x squared over x squared plus 1 still leaves us with the same denominator, same degree in the numerator and denominator. So we've got to do a little bit more with that. Now you can do polynomial division between that, x squared plus 1 into x squared. Or you can do what I've done here, and what I've tried to do is look at an idea of what I call decomposition. So x squared plus 1 minus 1 would be the same as x squared. So I can't change what I've got in the numerator in terms of the value of it, but I can change the way it looks. And then I can manipulate this to say, well, that's x squared plus 1 over x squared plus 1, and minus 1 on the x squared plus 1. So we've got it looking like that. So it comes down to 1 minus 1 on x squared plus 1 there, because those two will end up cancelling each other out. So there's our simplification. If you did polynomial division, you'll come down with the same thing. You get it going in once with a remainder of minus 1, so that gives you your fraction there. This time, again, a little bit different. So we're trying to get all the different types of questions we can see here. We've got the x minus 2 all squared there. Now that's different from what we saw before with the x squared plus 4. Remember we said that can't reduce down to linear factors. But this is actually a linear factor all squared times another linear factor. So it's a little bit different. So way we can do this, and the proofs are, if you want to go see the proofs of this, check out the textbooks, because they all give a nice proof of why this is the case. But when we've got repeated linear factors here, so x minus 2 all squared there, which is what we call a repeated linear factor, or the linear factors of a degree 2 is such there. So a double root type thing situation. So we have the idea that we could have a on the x minus 2 and then plus b on x minus 2 all squared. Now even though that's all squared, because it's a repeated factor, it's just going to be constants up there. As I said, you can look at the textbooks. They do a nice proof in the different textbooks about this. But just got to realise that when you do have the repeated situation, we have the x minus 2 to the power of 1 and x minus 2 squared. They're both going to be constants, because they're both factors of that one as well. And then it's just a constant over x plus 1. And then we're solving it as we did before. So we're multiplying through to get a to have a denominator, the first fraction have a denominator there. We have to have a multiplied by x minus 2x plus 1. And b only has to be multiplied by x plus 1. And c has to be multiplied by the x minus 2 all squared. So again, we've got our numerator equal to, the two numerators equal to, they're the equivalent statements. And then we're expanding and we're rearranging to get terms that we can play with. So we collect our ax squareds, so the a plus c is equal to 0. We collect our terms in x, so we get the minus a, the b, and the minus 4c, and that'd be equal to 2 because it's 2x, and minus 2a is a constant, b is a constant, and 4c is a constant. That's equal to 0. So we're able to get c in terms of a, and then we can find a B minus 4C. So we can put the C in for A there, and then get a statement, and we'll put B in and get B in terms of C as well, and then substitute those both in to get a statement in C. Once we've got a statement in C, we can get the values for A and B, and then write our partial fraction down there. So again, this is taking the one from the few questions there, where we've got a repeated linear factor and a quadratic factor that's irreducible. So x plus 2 all squared. So we said they're going to be constants on top for those two. But because that's irreducible, the numerator there can be a linear expression. So that's why it's a cx plus d. And again, we get back to a common denominator, and in terms of a, b, cx, and d, when that's all going to be equal to 1. And then we've got it. Really what we're left to do is just expand those out, collect our terms. Everything except for the constant will equate to 0. So we're able to go through and do that in terms of the cubes, the squareds, just the x, and the constants, to work through and get a in terms of c, and then we do the substitution so we can get a in terms of expressions in terms with d. So d works out to be 0, which makes life a lot easier. And then so that would be c, so we can get b in terms of a, and then start to do all our different substitutions. So check the algebra out really carefully, and that's what you've got to be careful with all that algebra. Lots of terms, easy to make mistakes, so you don't want to muck up one term and have it not work for you. But you come down to the 1/16 minus 1 on 16 and 1/8 there, so you're able to get down to the values that you need to solve that. And then, as I said, they're going to help us to solve some of our integration problems. So have a look through, be careful of the algebra, be wary where you see squareds, the linear factors being repeated, or factors where you have a quadratic that's irreducible. There's going to be the main challenges that you face with partial fractions, to make sure you set up the next step correctly so you can get your constants that are needed.